Now it's on. Cool. All right. So we're going to be switching modes a little bit and going back to talking about RNA, and finishing up our discussion with our final RNA target, which is a very well-known RNA. And this work was done with Riju, which is actually, he's the reason this challenge existed, because he encouraged us to use some of our previous research as a challenge. This is certainly one of the most daring experiments we did, and very glad to have predictors participate in this. So what RNA did we use? Well, we used probably one of the most well-known RNAs, and it has a very well-known fold, so the RNA part of this challenge was not a question. Just to give you some of the deep history of this, originally this RNA was found to be an enzyme by itself by Tom Scheck. He also did an MSA-based secondary structure and experimental secondary structure analysis. Way back in 1994, we already had negative stain images of what this RNA looked like. We had a bunch of crystal structures happen in the late 90s and early 2000s that gave us an idea of what the global fold was like. But it wasn't until 2020s that we were actually able to resolve the full structure with cryo-EM. It is too large and flexible for previous attempts at crystallography. And you can see we've had a steady increase in resolution, allowing us at these final stages to start to see magnesium binding sites. But when I joined the lab, we were sitting, work done by Haiming, Michael, and Shanshan. We were sitting on this higher resolution map of roughly 2.2 angstroms. So this is roughly when we can not only see magnesiums, but we can start to see water densities and other ions as well. And just showing you kind of the quality of data here, we can really start seeing the grooves created by the exocyclic groups in the bases. And not only did we have one map, we actually had two independent full maps. So these are not half maps, these are independent full maps of roughly similar resolution. And in the core regions, they're essentially identical. They're only differing by model in these flexible regions that you can see here are not even displayed because they're so flexible. So it gave us a really nice kind of cross-validation or independent maps to try to test out some different analyses of these extra densities. And this is what the extra densities look like. So if you remove the densities that are around the actual RNA atoms, you end up with some of these beautiful densities around the RNA. In dark blue is just high density values, and then you can see lower density values in the lighter color. And what I want you to notice here is the agreement between map A and map B. So these are likely not noise peaks. We're seeing consistent peaks between our two independent maps. So the first thing we did, and this work was done by Greg Pintelli, is to do the traditional. Look through the structure, try to find peaks in the map, and place waters, magnesiums, or other ions based on the geometry around that peak. And you can see some examples of these here. But then when I looked at these automatically placed waters and ions between model A and model B, there was something concerning that popped up. So here I'm showing the two models and just coloring the waters and magnesiums by whether they agreed between the two models. And what you can see in the summary tallies here is only roughly 50% of the placed waters and ions agreed. So the question was why? So when I asked cryo-EM specialists, they told me, okay, maybe it's actually different water structures, right? Maybe it's actually this conformational change in this distal region is causing different structures in the core. When I asked RNA specialists, it had to be noise in the cryo-EM data. So both of these hypotheses would mean the map would look different in these regions of disagreement. So we went back to the map and tried to figure out if this was true. So what I'm showing here is these kind of darker dots in green and red are the actual modeled waters and magnesiums respectively. And then the red density is other cryo-EM data that was not modeled. So what you can see is in regions of disagreement, such as this right top-hand corner, where map A has a water modeled and map B does not, the maps essentially look very similar in most regions of disagreement. So neither hypothesis ended up being true. What ended up happening is most of these disagreeing modeled waters were actually in regions of diffuse density. So regions where there wasn't a super ordered peak. So in one map, it passed our criteria of being an ordered peak, and then the other map, it did not. But overall, the densities were very similar. So this led us to thinking, okay, maybe all this density that we don't model because it's not a sharp peak, maybe that's actually telling us something about the water network or the ion network in our RNA. And here is just a video to prove that it's not just this snapshot. I showed you that there's similarity, but there's similarity across all networks in this core region. So we did quite simple molecular dynamics simulations on this RNA to investigate whether this would help us understand whether these low diffuse densities we were seeing were actually real water networks. And what you can see is we have some regions, for example, this network of waters here, that have some agreement with the cryo-EM maps. So that gave us extra confidence that these may be real interesting signals. But you also see regions where, at least in our molecular dynamics simulations, we were not able to reproduce the densities. So this led to the challenge. So the challenge was to predict the ensemble of the solvent shell out to 5 angstroms. We told them not to assume any large dynamics. We're really looking at the core that's well structured. We told predictors the buffer conditions, any information we thought would be pertinent. And then we told them that we were going to be doing local alignment and only comparison to maps. And we ended up receiving 360K atoms. Sorry, that should be million atoms. So I think we ended up receiving a lot of the Andre's billion atoms for this challenge. But most of them are water. It's a little easier to deal with. And a majority of predictors submitted the full 1,000 models that we allowed them to submit as a full ensemble, with some predictors submitting fewer, and some really submitting ones with only ordered waters or magnesiums. So how did we actually assess this? Well, our first step was just to convert these atomic models to densities. So we parsed out all the waters and solvents. This was a very key step of aligning by each residue locally. So because water structure is a local phenomena, we went residue through residue, took the 10 angstrom neighborhood and did an alignment there, and then combined all those locally aligned densities together to create a single local density map. And then this is what the single local density map ends up looking like. You can see the reference RNA where all these densities have been aligned to in blue. And then you see nice water patterns around where we expect water to be, for example, just due to electrostatics throughout the helices. And then we take these densities for every group and we score against the actual cryo-EM density. So the simplest scoring we can do is just simple cross-correlation. So that is what you're seeing on the y-axis. And this graph is cross-correlation in the region that's 1.8 to 3.2 angstroms away from any RNA heavy atom. And what you can see here is that we have okay correlation. This is actually higher correlation than our in-house MD simulations. They are roughly here. And we have 4 groups kind of up in the top region here. I just want to note that I won't be showing it here, but we did do robustness tests on the radius of that shell we were looking at, as well as different relative scattering of water, sodium, magnesium, other ions that people predicted. And all 4 of these teams that I point out did some sort of MD-based method, a variety of different force fields. But important thing to compare to is our experimental error, right? So this challenge was nice because we had those 2 independent maps. And if we do the same calculation for experimental error, we are well above what we were capable of for prediction, offering lots of space for improvement in the future. So to look locally, we can do the same correlation scores in a local region. And there's 2 residues that came out as interesting when comparing the two groups that we'll be speaking today. U170, which is this guy here, that's the start of this stem that continues this way. And then if we go upstream, the RNA does a very sharp bend here in the backbone to U168, which will be back there. We have two densities in this U170 region that are quite ordered, so we don't see very much diffuse density around them. And then in this backbone region where it kind of loops around, we have a very large diffuse density between the backbones. So what did the two groups you'll be hearing from today do in these regions? Well, to start with the ordered waters, the Bussy lab reflex came up as being a better score in the region of U170. And this is because they predicted a much more discrete water density here than Southern RNA did. Whereas Southern RNA did better around U168, which is this backbone region. And that is because they predicted more diffuse density there. So our correlation is telling us something about comparing the density to experimental data. We can also do a classification-based ranking. So if we essentially take our experimental data and say we want to have you predict everything that is above 3 sigma in density value, we take these as our positive voxels, so voxels that we think predictors should predict an ion or water in. And then we ask, do predictors successfully predict these density predictions? And we can do simple ROC curves for this and calculate the area under the curves to get a comparison between teams. You see here for this kind of lower density values that we actually have very similar performance between teams. So I'm just plotting those top 4 teams here for simplicity. And experimental error is this black line here. So we have a large room for improvement again. And if we go and we change the densities we care about to only the most ordered of density here, we see we get more separation between the teams. And we actually, once we go to the most ordered densities here, we have Southern RNA beating out the rest of the teams in this metric. And we can plot this summary of the area under the ROC curve for different essentially order metrics in the experimental map. And we can see the two teams that we'll be talking today. The Bussy lab reflex is here and Southern RNA here come out on top with Southern RNA predicting the most well-ordered positions, but not necessarily doing the best on the least ordered position. So to quickly conclude, we were very surprised to get 25 predictors in this first of its kind experiment. The primary participants and the good performers, but that may be just because of the selection of teams we did have, all came from the MD groups. Local alignment was vitally important for assessing the water and ion ensemble. And while there were differences in the MD methods, there is much room for improvement, potentially assisted by similar data and blind challenges. The other thing to note is this data and predictions is certainly not, there's plenty of information to be learned from it. So we hope both predictors and ourselves will continue to look at these data to find new information, including potentially looking at ion identity and waters and ordered positions. So brief acknowledgements to the organizing team for letting us do this challenge, and the experimentalists for giving us a chance to use the data to do this challenge, and then the predictors for giving it a shot and providing great data.
Thank you so much. We'll have time for questions.
Rachel, thanks. It's great. My question is about your map. Is it possible that you have mixture of water in the same map, even though the map is high resolution? So some of the waters are actually coming from multiple 2D images. That one of them has the water molecule here, and one of it has the water
Yes.
molecule here, and we actually
So I think that's something that we can discuss more in the discussion session. But as of now, right, this is essentially an ensemble average of all the particles we're looking at. But ideally, we would go back and compare it to particle stacks in some way. So we'd actually be comparing to individual particles and getting some sense of occupancy in that way. It's never been shown you can do that for something like water and at that small scale. So it would definitely take some validation.
would have mentioned.
But that's definitely a direction we could go, yeah.